So I'm going to carve them out, and you can just unmute and name it if you got the guts to do it. No, I'm just joking. Anybody? What functional group is that?
Amide.
Good. Let me switch pencils. It's an amide. Good. What about here?
Alcohol.
Alcohol. Good. Come on, Russell. By the way, this molecule is Taxol. It is a anti-cancer medication. It is actually, before my wife passed, this was the first drug they gave her. She passed away from breast cancer. So this was actually the first drug that they gave her. And me being the chemist, whatever they gave her, I was looking it up, trying to see what the functional groups were and how it potentially interacted. Because no matter what you take, it's going to fit into some type of receptor, or it's going to either enhance a pathway or disrupt a pathway, no matter what it is. The drug itself is taken from the bark of the Pacific yew tree, but even if you take that tree takes 100 years to grow back if you cut it down and harvest the bark. So that's one problem. The other problem is you only get a few milligrams, even from the bark of an entire tree, you may get a few milligrams. Now you take that and think about how many cancer patients you're dealing with in worldwide. That's not enough. So two groups actually undertook like the synthesis of Taxol. One group was at Florida State, one group was at Harvard. The Florida State group, I think they finished first, and they ended up selling the license to their synthesis to either Bayer or Bristol Myers, and they get royalties off this. Like I say they, but the PI, I think his name was Robert Hoffman. He gets royalties off this every time it's sold. Plus, he sold it for a couple of $1 million. He sold a license to the pharma company so that they can make it on large scale. But so that's just some practical applications of chemistry. It's everywhere, especially organic. What about the one I just circled? Anybody?
And aromatic.
Aromatic, good. All right, what about here?
Is that a ester?
Yes, excellent. So ester. What about here? And this will be in the notes today, so don't worry about trying to draw this thing out. You'll have the information. Anybody? Isn't that the same structure that we just looked at? The same motif?
Is it an ether?
Well, okay, so if the carbonyl wasn't there, it would be an ether. But because of that carbonyl, this is also an ester. Can you see how these look alike right here?
Yes.
All right, what about here?
Alkene.
Say again?
Alkene.
Good. So alkene. Here.
Is that a ketone?
Excellent. It's a ketone. We didn't really talk about ketones, but I know it was in the video, ketones, aldehydes. I think I had a video with just all carbonyls in it. But yeah, it's a ketone. What about this one? It's a It's an oxygen.
Ether.
Good. Right, it's the oxygen suspended between two carbons. That's exactly right. Everything else is like kind of the same here, right? You got another ester here, another one here. As a bonus assignment, I may post the actual publication from where this was when this was first synthesized by the Hoffman group, and just ask a few questions out of the paper and let you kind of start getting a handle on dealing with publications and reading the literature, because that's very important as a scientist. You got to read the literature to keep abreast on what's happening. So I may post that later today. All right, you can also see here another alcohol here, and more aromatics. But again, I can't stress enough for you to pay attention to. Let me change colors. Pay attention to these markings, right? That wedge line means that group is going back into the page, and I'm sorry, dash line, the wedge line means it's coming out of the page. So everything you see on a dark wedge, think about it facing you and coming out of the screen at you. And everything you see on a dash, think about it going away from you back into the page. That is what we call stereochemistry, right? Let me write that down. Let me pick one that's kind of out of the way. That's stereochemistry, or another way to describe it is the 3D orientation. It's bad. I don't want this to be junky when you look at it later. I can move this. Right, so when you have a defined wedge or a dash, that's my stereochemistry. It's the 3D orientation, right? And it gives this molecule a shape, right? You might think that's not important, but when this binds to whatever receptor is going to bind to disrupt tumor growth or proliferation, it does matter, right? And to think about this in terms of how it interacts with the body, right? There are, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 stereo centers. Every one of those wedged and dashed lines, we call those stereo centers. There are 12 of them. So there are 2 to the 12 possible stereoisomers for Taxol, but only one of them works. And that's the one that if you synthesizing it, that's the one you have to make in order to achieve the goal of disrupting tumor growth. So whenever you see something this complicated and this with this many stereo centers, just know that it takes a lot to synthesize something like this. And it also, the other part of it is you have to have specific types of reactions that you can do to set those stereo centers, right? So that's just some more functional groups, but also just some good information for you to have as far as like why we're doing this, why we're even studying this. If you're a biology major, if you're a chem major, if you're going to pharmacy school, med school, wherever, these types of things matter, right? Which isomer works, which one doesn't, so on and so forth. All right, so now we got to switch gears. I'll move that up too, by the way, up to, but I'll do it after class. We got to switch gears now. We've been talking about functional groups and how functional groups give functionality to molecules. So now we're going to switch gears. Today's not the ninth. And we're going to talk about resonance. Right. So resonance is really kind of a, it's a term that we use to describe mainly what we call delocalization. Hopefully you watched the videos that I sent. If not, you can watch them today. Of electrons. Right, but the term itself is murky, right? Because from resonance, you get resonance forms, which are basically averages of the Lewis structure of a given molecule, right? So so resonance forms depict all possible. I'm just going to write it like that or define it like that. It's a kind of a bootleg definition. So all possible Lewis structures for a given molecule, right? So those resonance forms are going to be different. What the way we're going to attack this is we're going to look at this based on three types of systems, and that's going to simplify everything down to nothing, right? So let me give you an example before we look at the systems. So if I have something like this, right? C double bond O, and I have a carbonyl here on the outside, and I'll just say CH3. This is one way to depict this structure, right? And the functional group, the carbonyl functional group here, this is a ketone, by the way. That functional group makes it possible to have another way to depict this, right? So you have this way, and then you have another way. And I'm just going to draw it without explaining it, and then I'll explain it later when we start talking about the different systems. So the other way is to take that pair of electrons and delocalize them or share them here, right? So this is the path that those electrons can travel to be shared between those three atoms only. This atom is excluded. So it's excluded from that. So the way I show it, anytime I'm doing resonance, anytime I have a resonance problem that I'm working, is I'm going to use, and this is for all organic, we use curved arrows to show electron movement. Right. Anytime we move electrons, we use curved arrows. The type of arrow is going to be dependent on how many electrons we're moving. So if I'm moving 2 electrons, I use a double-headed arrow like this. That means I'm moving 2 electrons. If I'm moving 1 electron, then I use a single-headed arrow. That's the convention. That's with resonance, or if you're doing a mechanism, or any time you're showing the movement of electrons, you have to use what we call curved arrow notation. All right. So I'm going to show this, and then I'm going to explain it using some ideas that we've already covered. All right. So this is how I would draw the resonance form for this. I would take this pair of electrons, I'm going to move them here. What that means is that I'm moving those electrons between these 2 carbons, and that's going to give me a pi bond right there. Don't panic, because I'm going to explain the systems and all that stuff, right? And then if with the central carbon right here, unless I change something, that carbon has a problem because it's going to have 5 bonds to it. Let me put some electrons on oxygen. So then I can take that pi bond, and I want to take those electrons and give them to oxygen using a curved arrow. All right, so now my resonance form is going to look like this. So now I got a double bond here between these two. And now I got 3 lone pairs on oxygen and a negative charge. If you'll notice, the charges are consistent. The charges stayed the same. So the overall charge on the top structure is negative. The overall charge on the bottom structure is also negative, right? So that doesn't change, right? And I have to, again, obey the octet rule. Carbon can't have 10 electrons around it, so I had to break a bond. So in this case, I broke the pi bond, right? So when I look at these two structures, there's a, if I were to draw what the intermediate or the average structure looked like, it would look like this. Where I would show the electrons. Let me just switch pens right quick. I would show the electrons kind of shared over those 3 atoms like that with a dotted line, meaning the electrons are moving between those 3 atoms. So this is what we call a resonance hybrid. All right. Any questions so far? I'm going to explain everything, so don't panic. So the hybrid is like an average of those 2 structures, right? Where the electrons are kind of shared. It shows you where the electrons are shared, which atoms are sharing the load. If you watch the video, I talked about taking a charge and spreading it out over multiple atoms to decrease its intensity, right? Or to decrease electron density, because atoms don't like holding charges. So if they can delocalize the charge over multiple atoms, then that's great. But it can't delocalize anything unless there's a specific scenario that's set up. All right, so let me show you this from an orbital perspective. Right, so here, this carbon, it has that lone pair and a p orbital. And then the carbonyl carbon, you got a sigma bond between carbon and oxygen, but you also have p orbitals to make up that pi bond, right? So you got p orbitals to make up the pi bond. So each one of those atoms, again, if you recall, when we talked about hybridization, we talked about sp2 carbons, right? This is a sp2 hybridized atom, so that's sp2. Oxygen is also sp2, right? We talked about the fact that one of the p orbitals is left unhybridized, and that's where your pi bonds come from. So the p orbitals here in the carbonyl are aligned with the p orbital on that CH2, right? So everything here is in alignment. That's the only way you can share electrons, is if you have orbitals that are aligned and able to overlap. Right? That's the only way you can do this, is to have those orbitals lined up and able to overlap. Are y'all following that? Any questions about that? If I drew it out in 3D, it would look like this, right? Where you have a p orbital on each one of those carbons, or on each one of those atoms. So this is the oxygen, carbon, and carbon. Right? So in order to do resonance, orbital overlap has to be possible. That's why this carbon is not involved, right? Because this carbon doesn't have an orbital that's overlapping with that system. So you can't involve it. All right, so let me show you now the 3 different systems. Right, 2 of them are two of them are what I'm going to call allylic, and one of them is diatomic. All right. In the video, it might have said a 3-atom unit or a 2-atom unit, something like that. So an allylic system would be something like, I'm just going to use all carbons. So that's what we call an allylic anion, right? Allylic is this position right here, right? It's right next door to a double bond. That's what that means, right? So you have an alkene, and then right next door to it, you have some functional group that can donate to, right? So you need two things to happen for resonance. You need orbital overlap, which every allylic system is going to have, and you need another. The other part of this is that you need what? Somebody tell me what the other part is. What do you always have to have in order to do resonance? What two things have to be connected? Anybody? I know it was kind of late in the afternoon when I sent that resonance video, but if you watched it, tell me what else you need besides well, that's going to be a consequence of that system being the way it's structured the way it is. Anybody? All right. So the other part is that you need a donor connected to an acceptor. They have to be adjacent. So when you look for opportunities for resonance to happen, it's all about pattern recognition, right? If you see the allylic pattern, you know immediately that you can do resonance, all right? Whether it's an allylic anion or cation. So a donor can be a pi bond or a lone pair. You'll find out later, sigma bonds can also be donors, but they're not donors in the sense of resonance. They just, sometimes you can use the electrons in the sigma bond to make another bond, but we're not going to get into that. So you can have a pi bond or a lone pair. That's a donor. And then your acceptors can be, a pi bond can play both roles. You can have a pi bond or a carbocation or cation, right? And they have to be linked. So they have to be adjacent to one another. So up here, this is going to be my donor, right? And then my pi bond on the other side, this is my acceptor in this system. And you're going to find out every resonance example that we look at, the example is going to fall into one of these three categories. It's either going to be an allylic anion, it's going to be an allylic cation, or it's going to be a diatomic system where it's two atoms next door to one another. All of the examples are going to fall in that category. All right, in one of those three categories. So this is my donor on the right, and then my pi bond is my acceptor on the left. And again, the fact that the alkene functional group consists of a sigma and a pi bond makes it an acceptor. It's able to accept electrons, right? And when I say donor and acceptor, I'm talking about electrons. So it's either an electron donor or an electron acceptor. All right. So anytime, this is 100% of the time, your electrons are always going to move from donor to acceptor, always, never the other way around, right? So here, I'm going to take the electrons that are on this carbon and move them here. This is standard. If you can grasp this, it does not matter where you see the example. It's the same identical process. The lone pair is going to become a pi bond here. That's going to make a pi bond between those two carbons. When that happens, this pi bond is going to break and become a lone pair for the allylic anion. All right, questions? And so what the resonance form is going to look like is that pair of electrons is now going to be on the other end. So let me move this down so I can draw the resonance form. And you always put a double-sided arrow between the resonance forms because they're interchangeable. So this is C. That's negative. This is CH, that didn't change. And then this is, now the double bond is on this side. Right, and they just go back and forth between those two structures. All right, questions about that? So in order to do resonance, you need orbital overlap. Another way to say that is you need a donor and an acceptor adjacent to one another. Because again, the orbitals can't overlap if the atoms are too far apart. Right. All right, let's look at the next system. So system number one is a allylic anion. Number two is also a allylic, but it's an allylic cation. All right, so in this case, my cation, because it has a positive charge, that means it's electron poor, it's electron deficient, it's my acceptor. Right, so electron acceptors are always what we call electron poor. Right, they need electrons. So anything with a positive charge is missing electrons. That means that it can accept electrons. All right. So now, in order to delocalize that charge and share it with the other atom down here, for the allylic cation, what I do is I take the pi bond and I just shift it over to here, just like that. So now, resonance form is going to look like this. So this is that CH2, it's now positive. This is CH, and now the double bond is on that side. And again, that double-sided arrow means that these are interchangeable. They just oscillate back and forth. Unless one of them is more stable than the other, they go back and forth between the two structures. And anytime you do resonance, the more times you can do it, the more stable whatever the structure is that you are that has the charge or whatever. Stability increases with the number of resonance forms that are possible. All right, we're going to talk about that down below. All right, so you got a allylic anion, allylic cation, and I didn't write that. Let me write that here. The pi bond in this case is the donor. Remember, your donor can be a pi bond or a lone pair. Your acceptor can also be a pi bond or a cation. So the pi bond is an acceptor if it's adjacent to a donor. It's a donor if it's adjacent to an acceptor.
Can you say what to look for if we're trying to find the acceptor again?
So a plus charge, or
Okay.
a plus charge can be an acceptor or a pi bond. So your pi bond, if it's next to an acceptor, is going to be a donor, and then if it's next to a donor, it's going to be an acceptor. we're going to see a lot of examples of this, right? All right, there's another allylic system that I'm going to show you real quick, but it doesn't involve two electrons, right? You can also have a single electron here. We call that an allylic radical. A radical is just a species with a single unpaired electron. Right, so a single unpaired electron. So with this, what type of arrow do you think I'm going to need to show how these electrons move? Right, if my cation and my anion, if I used a double-headed arrow to move two electrons, because every bond is made of two electrons. With a radical, I have to use a different type of arrow. I need an arrow that's indicative of one electron at a time. Are y'all following? Anybody not catch that? All right, so if I have an allylic radical like this, I'm going to show the migration of that pi bond this way. All right, so one electron is coming here, and then I'm going to bring one from here, right? That single-headed arrow means I'm moving one electron at a time. Right, I have had students in part 2 that still try to show radical processes with double-headed arrows. So you always use a single-headed arrow when you're doing this. And then the other electron, the pi bond, is going to go here. Right? Look at what happened to the pi bond. I broke it. Is that right? I took the electrons in it and I'm redistributing them. That's what those arrows mean, right? When the tail is here, that means I'm taking an electron from there and the head is over here. So I'm moving it to another location. Same here. If the tail of the arrow is here, that means I'm moving that electron from there to somewhere else, which in this case is going to be here. Same thing here. Tail of the arrow is where I start. The head of the arrow is where I want that electron to go. So I'm still doing the same thing. I'm still putting a pi bond right there, right? And on the other side, I'm breaking that pi bond. So this is what that resonance form would look like. All right. Questions about that? So you can have an allylic anion, you can have an allylic cation, you can have an allylic radical. And it's not limited to carbon. The allylic system can contain any types of atoms as long as they meet the criteria for being allylic, meaning you have a pi bond that's next to a donor or a pi bond that's next to an acceptor. All right, questions? Any questions? All right, let's look at this last system. So all these are allylic. And then the last system is what I want to call a diatomic, just contains two atoms. So in this case, I'm going to say that I'm just going to use a carbonyl as the example. All right, I can push this pair of electrons here. And now the electrons in that pi bond are now given to oxygen, and that's negative, and then this is positive. So these diatomic systems are going to have either a pi bond between them, or they'll have like two charged atoms that can, well, one is a donor and one is an acceptor. So in this case, you see that this is the donor, this is the acceptor. So if I push the pair of electrons back here, I get the original structure back, right? And up top, you can see that you can tell by the how the arrow is drawn from the pi bond to oxygen that the pi bond is the donor and the oxygen is the acceptor. All right, so let's jump in and do some examples because this is boring, right? We want to see some action. So let's go to here. And let's start out with A. I'm actually going to cut this out because I don't want to try to squeeze this in and have it looking all jumbled up and crappy. So I'm going to copy that. Let's start with A. A is a great example because it's going to give us an opportunity to show an exception. All right. So and let's go back to the question. The question says supply the arrows to convert between resonance forms. So we got two structures. Let's start with the one on the left. All right. Do you see an allylic type system anywhere here? Let's start here. All right, we got an alkene right here. And then adjacent to it, we have a carbon that's a part of a carbonyl. So in this case, this is still considered, it still falls in the category of an allylic system, right? But if we were to put resonance arrows in, so let's say that the alkene is the donor and the carbonyl is the acceptor. And you can see that they're connected by a bond between them. So the donor and the acceptor have to be adjacent to one another. They got to be connected so they can overlap orbitals and share electrons, right? So if I take the donor and donate those electrons up to here, what happens to the carbon oxygen pi bond? What do I have to do to that?
Would you move it up to the oxygen?
I would move those electrons here and give them to oxygen. So this is what the resonance form looks like or should look like. That's negative now. Nothing else changes. I'm only moving electrons. I'm not breaking bonds. Well, I'm not breaking sigma bonds and I'm not rearranging the structure. I'm just moving electrons between the donor and the acceptor. So now that's that. And then this carbon right here had a hydrogen. So because I broke that pi bond to it, I made that carbon electron deficient. Now it only has 3 bonds. So I'm going to put a plus charge on that carbon. All right, so the overall charge is still going to be negative. I'm sorry, neutral. Right? So compare this to that. Is that a resonance form of the original structure, the one that's on the right? Let's think about it now. Let's say this is my donor. Where should the acceptor be? If the donor and this is my acceptor, is it close enough to overlap with the acceptor?
No.
No. If my donor is here, my acceptor needs to be on the next carbon. That's how it works. If it's not, if they're not adjacent, you're not going to get resonance. I'm putting should in all caps. Right, it should be there, but it's not there. So this is an example of that's not a resonance form. And you cannot go from the structure on the left that we showed to the structure on the right. So this will never happen. All right. I wanted to do that first on purpose because I want you to see that in order for resonance to happen, it has to be a very specific set of circumstances. You got to have a donor adjacent to an acceptor, period. All right. Let's take another one from up here. Any questions about that before we move to another one? Let me take this one. Right. So how do we get from here to here? Because you can do resonance there. Right. What changed going from the structure on the left to the structure on the right, and how do we show it? Let's put some electrons in. Right. Where's my donor? Where's my acceptor? Let's start on the left. Where's the donor? Where's the acceptor? What do you think? Something that has a negative charge, that has a negative charge and lone pairs to give, there's no question that this is going to be the donor. It's giving away electrons, right? And then that carbonyl carbon, because it's bonded to that oxygen and there's a dipole here, it's polarized, right? So those types of functional groups with that type of polarity always serve as acceptors. So how do I show the migration of the pi bond? Because now I have a pi bond here in the resonance form. How do I show that starting with the structure on the left? Anybody?
On the left, the curved arrow. I mean, you draw a curved arrow from the pi bond to the. No. Okay. Yeah, you could do that too, and then you draw a curved arrow from the pi bond with the C up there. Yeah.
Okay. You always, and again, with this, what pattern does this fall into? Let me ask that question. Look at the pattern. It's negative, so it's an anion, right? There are 3 atoms, and the anion is right next to a pi bond, right? So this pattern falls into that class of compounds that are what we call allylic anions, right? And because it's an allylic anion, the electrons are only going to flow a certain way. They're going to flow from the donor to make a new pi bond, and you're going to end up breaking the pi bond that's in the acceptor and giving those electrons to one of the atoms, to the terminal atom in that acceptor, right? If this is my donor, that means this is my acceptor. All right, and that's how I get to this structure over here on the right. Now, how could I go back to the structure on the left, starting here? Like, it's still an allylic anion. Nothing changes about that. So how can I go back the other way? This is the donor. This is the acceptor. How can I go the other way? Anybody? Can I do this? To go back to the other structure on the left? The answer is yes. we out of time, but we'll pick this up on Wednesday. And then on Thursday, we'll work through some more examples too, during recitation. I'm gonna try to do it Thursday at 6 o'clock, same Zoom link. So we'll try to do that this coming Thursday at 6. All right, any questions before we sign off? I know I'm over time.